Welcome to this course on partial differential equations. In this lecture, we are going to discuss some basic concepts and the nomenclature that is involved in the study of partial differential equations. So, the outline of today's lecture is first we discuss certain preliminaries, then we go on to define what is a PDE and what do we mean by solution of the PDE, and then we discuss classification of partial differential equations. So, study of partial differential equations involves functions of several variables, theory of differentiation and integration for such functions. Therefore, let us discuss what are the domains of those functions are going to be. So, we consider functions defined on an open subset omega of Rd. Since we are studying partial differential equations, functions are of several variables, therefore, d is greater than or equal to 2. We use the notation omega d to remind us that the set is contained in Rd, because later on we are going to see that in a certain problem we will see many sets. One is lying in a higher dimension and one is lying in lower dimension. Therefore, this will keep track or it will remind us that we are in certain dimension. So, an element of Rd x is written in boldface. It is not difficult, it is not easy for us to write on paper, but in print it is possible. So, the boldface x actually stands for a d tuple of real numbers x1, x2, xt. We may also use normal x in Rd, and there should be no confusion, because the moment you know you are dealing with functions in Rd and you have a function, let us say u of x, it means x is a d tuple. So, writing x takes more time and effort than writing a very simple x. So, when working with functions defined on subset of R2, elements of R2 will be denoted by xy. That is the standard practice, and we will not use x1, x2, we stick to the standard notation xy. Similarly, when we are working with the functions defined on R3, we use the notation xyz, the 3 tuple is denoted as xyz instead of x1, x2, x3. And in the context of PDEs, the variables x1, x2, xd, these are called independent variables. Now, we have discussed the domains of functions, let us discuss the codomains of the function that we are going to deal with. So, codomains of functions means the function where the values it takes. So, we assume that the functions take values in Rp p greater than or equal to 1. That is, we consider functions u defined on omega d. I need not tell you that omega d is a subset of Rd again, because the notation tells us, and takes values in Rp. Thus, the function u consists of p real valued functions defined on omega d, and we use this notation u equal to u1, u2, up. So, the function u is given in terms of the sometimes what is called coordinate functions u1, u2 etc. up to up. In partial differential equations, u1, u2, up are called dependent variables or unknown functions. In our course, we are going to deal with PDEs which have only one unknown function, that is only one dependent variable, in other words p equal to 1. So, the PDEs that we are going to study in this course are going to be a single equations. There is only one unknown function, not systems. Some more notations. Let u be a function defined on omega d taking real values. Then first order derivatives, the notation we use here is du. It denotes all the first order partial derivatives which are described here, dou e by dou x1, dou e by dou x2 up to dou e by dou xt. Then the second order derivatives are denoted with d2u. This is the notation. d2u stands for all second order partial derivatives of the unknown function u, which is dou to u by dou xi dou xj, I and j vary from 1 to d. Now, in general dku for k greater than or equal to 1 denotes all kth order partial derivatives of u. So, recall that the notation dku stands for the collection of all kth order partial derivatives. However, we need a notation for any specific kth order partial derivative. Therefore, we are going to introduce that notation. To do that, what we do is, let us fix a d tuple of numbers which are either natural numbers or 0. That is, alpha is a vector which is equal to alpha 1 up to alpha d. Okay. It is a d tuple. Where does it belong? N union 0 power d. That means each of them is a whole number, either a natural number or 0. For such an alpha of d tuple of numbers, whole numbers, we denote mod alpha equal to sum of the alpha i's. So, mod alpha equal to alpha 1 plus alpha 2 plus alpha 3 up to alpha d. So, the notation d alpha u means I am going to differentiate u with respect to x1 alpha 1 times, with respect to x2 alpha 2 times, and so on up to with respect to xd alpha d times. So, that is the notation here, d alpha u, where alpha is not a natural number or a whole number, alpha is a d tuple of whole numbers. D alpha u is equal to dou mod alpha u divided by dou x1 alpha 1, dou x2 alpha 2 up to dou xd alpha d. Let us see an example. Assume that d equal to 4, that means we are dealing with functions of 4 variables. So, the independent variables are denoted by x1, x2, x3, x4. Let us take alpha equal to 0, 2, 1, 3, and we want to differentiate u this alpha d alpha u. What is that? It tells us that do not differentiate with respect to x1, with respect to x2 differentiate 2 times, with respect to x3 differentiate 1 time, and with respect to x4 differentiate 3 times. So, sum of the entries of alpha is 6, 0 plus 2 plus 1 plus 3, that is 6. That means what it defines is a particular 6th order partial derivative of u. So, d alpha u is dou 6 u by dou x2 square, because the second entry here is 2, that is why second variable differentiate 2 times. Third entry here is 1, therefore differentiate once with respect to the third variable, and similarly with respect to x4 variable differentiate 3 times, because there is a 3 here. So, there is a room for confusion because we are using dku as at the top of the slide to stand for collection of all kth order partial derivatives, and here also d alpha u to denote this particular partial derivative. But there should be no reason to be confused, because this dku stands or makes sense only when k is a natural number. This d alpha u makes sense only if alpha is a d tuple of whole numbers. So, there is no room for confusion here. So, the order in which partial derivatives are taken does not matter. For example, if I want to differentiate with respect to x3 first in the above example and with respect to x2 later, there is no way to take care of that in this notation. In other words, this notation does not care the order in which you take the differentiation, which is not okay. We know that partial derivatives do depend the order in which they are taken, but for reasonable functions they coincide. So, we are going to consider such functions only where the order in which you differentiate does not matter. Okay. For example, if you are considering a C2 function, then it does not matter in which order you differentiate. That is a theorem in multivariable calculus. Maybe that is the reason why this notation does not respect the order in which you will differentiate. Now, let us go to the definition of a partial differential equation and what do we mean by its solution. One normally says PDE is an equation involving partial derivatives. This can be accepted as a definition provided we understand this statement. Not only that, everybody understands this statement in the same way. Question: what do we understand by the above sentence, right? We are saying involving partial derivatives. So, question is how many derivatives? Finitely many or infinitely many is also allowed? There is one question there. Second question is, what does the equation involving stand for? What does that mean? No idea. However, we seem to be knowing examples of PDEs, therefore, we do not question this kind of a definition if found, we do not question, because we know what are PDEs, we know. Okay. So, how do we know? We have examples and this English statement seems to be okay, but the problem is this English statement might allow more types of equations which you do not think is a PDE. We will see one of them as an example. Okay. Therefore, these are the examples that we seems to be knowing. Dou u by dou x plus dou u by dou y equal to u dou u by dou x plus dou u by dou y equal to 0, and another equation dou 2u by dou x square plus dou 2 by dou y square equal to sin x plus cos y, and so on. Many such examples we know. And the above sentence, PD is an equation involving partial derivatives, seems to be acceptable. Okay. Therefore, there seems to be an answer to the first question, that means how many derivatives should be there in an equation, because whenever we are writing an example of a PDE, we are not thinking of writing an equation which involves infinitely many derivatives. Therefore, we know that a PDE should have only finitely many derivatives appearing in the equation. What about second question's answer? Still no idea. So, we need to capture what we are writing here in terms of some definition, which is very rigid. Okay. So, in mathematics, as we know, definitions are set in stone, and vaguely worded sentences are not allowed as definitions, such as this: PDE is an equation involving partial derivatives. So, we reformulate the above sentence, or rather we give a mathematical meaning of this sentence or a possible mathematical meaning of the above sentence, and once we write down as a definition, we stick to that. That is a definition. Okay. So, we understood that PDE will have only finitely many derivatives in it. Therefore, find out the order of the derivatives which appear in the equation, look at the equation, ask which the derivative appears, and let M be the largest having the above property. Being the largest, it will be unique, and this largest derivative which appears, largest order derivative which appears in this, that particular order is unique, and that is called the order of the partial differential equation. So, now we need to define. A PDE may be defined as an equation satisfied by all partial derivatives up to order m, including the function as well. Okay. So, a relation of this type, capital F of x u du d2u dmu equal to 0. Recall what is du? Collection of all first order derivatives. D2u collection of all second order derivatives, and so on. This is collection of all mth order derivatives. So, for some m and some function f, we should be able to cast our equation in this form. Now, where x is in omega d. Questions: what is m? What is the domain of f? So, m is the order of the PDE. Okay. So, this is how we plan to define. We can, if you have a PDE which involves only first order, you can also think I can write this equation with m equal to 2, but such a thing should not be allowed. Our definition will not allow, because this m, we would require that m should be the order of the PDE as identified on the last slide. M is the order of the PDE means some mth order partial derivative appears and no higher order partial derivatives appear in the equation. That is why that m is unique. And now, once you know this, it must be easy to write down the domain of f. Once you see the equation, it is easy to write. Let us look at some examples. Examples, it is always easy. Okay. So, for this PDE, dou u by dou x plus dou u by dou y equal to u, m is 1, that means first order PDE. So, first order PDE means it has to be expressed as x, y, u, du equal to 0. Du means all first order partial derivatives, which are dou u by dou x and dou u by dou y. So, it should be written in this form. What is f? F should be some function of how many variables? 1, 2, 3, 4, 5. F should be a function of 5 variables. So, this is always a good practice to write any such function like this. F is f of x, y, z, p, q. Okay. X, y is the independent variables. It means we are working with a PDE in 2 independent variables here. Z is the location where you are going to substitute u. P and q are the places where you are going to substitute for dou u by dou x and dou u by dou y respectively. Okay. It is important to stick to this kind of notation, understand this notation. So, what is f of xyz pq in this example? It is p plus q minus z. Therefore, if you take f equal to this and consider this LHS, that will become dou e by dou x plus dou e by dou y minus u, and hence you get the PDE. Now, largest domain on which this f is meaningful is R5, because it is defined for every phi tuple xyz pq, this function is defined. However, we may also consider the domain to be any open subset of R5, that is also ok. Observe something nice about this f. It is a linear polynomial in this variable p, q and z. Of course, it does not xy does not appear, therefore, it is still you can say it is a linear polynomial in all the variables. Okay. Let us look at second example. It is dou e by dou x plus dou 2 u by dou y square minus dou 2 u by dou x dou y equal to cos of y by x. What is the m here? It is 2, because the second order derivative appears and higher order derivatives other than 2 are not appearing, only 2, okay. 3, 4, 5 etc. nothing appears. So, m equal to 2. Once you have decided m equal to 2, what should be the f? F should look like this: x, y, u. This is corresponding to du, that is dou e by dou x and dou e by dou y, and rest corresponds to all second order partial derivatives of u. Therefore, f must be written like this. I told you x, y, z is the place we are going to put u, p, q for the first order derivatives, or s t for the second order derivatives. I have included s and s tilde just a placeholder for dou 2 u by dou x dou y and dou 2 u by dou y dou x. As I mentioned earlier, we are not going to really distinguish between these two. So, after some time we will not write s tilde, we will simply write f of x y z p q or s t. S tilde will be forgotten, we will not write that, because we will maybe we will consider functions for which both are same. For reasonable class of functions, this mixed partial derivatives coincide. And what is the formula for f? One can easily write down, it is this. Now, we will ask what is the domain of f? Then there is a problem here, because x equal to 0 should not be allowed, everything else is allowed. And what is the domain of f? It is how many tuples, tuple of what size? 2 here, 3 plus 2 first order derivatives and 4 second order derivatives. So, 2 plus 1, that is 3 plus 2 5 plus 4 9. So, domain of f will be in R9, but it should not contain x equal to 0. Okay, here I have written we did not, what I am saying is we will not distinguish. I told you what that means already. Okay, what is the domain of f? So, domain of f let us call omega 9, because it is sitting in R9 as we have written, because we have included f is a function of x, y, z, p, q or s tilde t. So, 9 variables are there. X equal to 0 is not allowed. So, that is what we say. Note that the given PD is meaningful for those x, y's in R2 for which x is not 0. So, if we denote the projection of omega 9 to the first two coordinates by omega 2, then omega 2 is an open subset of R2 which does not intersect the y axis. Thus, we may write the domain omega 9 to be like this: f is from omega 2 cross R cross R2 cross R4. This omega 2 stands for the independent variables x, y vary here. This R stands for the unknown function u, which we do not place any restriction on what values it must take. So, therefore, it can take any real number. R2 stands for the derivatives, the PQ variables, where dou e by dou x and dou e by dou y are going to come. R4 is all 4 second order partial derivatives. So, we can further write omega 9 in this form. Now, dou f by dou s is not 0. In fact, dou f by dou t is also non-zero. It means f is not a constant function in S, it means S variable is used by f, okay. It is not constant, it depends on S. It means it is a second order PDE. This guarantees that some second order partial derivative appears in the equation. So, now we are going to write the definition. let omega d be an open subset of Rd and let f be like this, omega d cross Rp and cross Rdp, d square p and dmp taking values in Rq be a function. So, it means f is taking values in Rq, that means there are q functions in this. Okay. This omega d is where x is going to sit, that means I am considering x in Rd. So, d independent variables, and this is Rp, that means the unknown function has p components u1, u2, up. It is a vector valued unknown function, and this corresponds to its derivatives because u is a mapping from omega d to Rp. Therefore, the derivative will be of size dp. dp many first order derivatives will be there. This will be corresponding to second order derivatives, and this corresponds to mth order partial derivatives of the unknown function. So, a system of partial differential equations. Why system? Because we are considering q greater than or equal to 1. So, there can be more than one equation, that is why in general we call it a system of partial differential equation. Order m, because we have d power m here, is defined by this equation. Okay. So, dmu all mth order partial derivatives which are so many. Okay. I am not discounting the symmetries like earlier I have done, I am writing full. Okay. So, where at least one of the mth order partial derivatives of u appears in the system of equations, only then we are going to say it is a mth order PDE. So, as I said, if q is bigger than 1, it is actually system of PDEs. Q can be equal to 1, then it is a single PDE or a scalar equation, and if p equal to 1, it is a single unknown function. If p is bigger than 1, unknown function is vector valued. So, now we have to define what is the solution of the PDE. A solution of the system of PDE which is defined here is a function. Solution is a function. When we say function with some domain. So, it is a function phi with domain u. Of course, here we have written system for vector variable, dependent variable is vector valued, therefore, this phi is also vector valued Rp with what property? U is a subset of omega d. What is omega d? Omega d is that set where this equation is meaningful for x belongs to omega d. The domain of f was omega d cross some things, right. But a solution can be a function which is defined even on a proper subset of omega d. It is a function with some properties. Okay. What should be the properties? All partial derivatives of phi up to order m should exist, including m, because I am thinking of a mth order equation. Therefore, all partial derivatives should exist up to order less than or equal to m. Second, once it exists, look at this tuple. I am going to substitute inside this x phi x, d phi x, d2 phi x, dm phi x. Therefore, I would require that this tuple belongs to the domain of f, and I have the right to apply f to that. When I apply, I get 0. That means this equation is satisfied in this way by this function phi. Note phi, we are demanding that it should be defined on a subset of omega d, and we are not demanding that it should be defined on omega d. That is very important to be noted. So, we do not insist that a solution must be defined for every x in omega d. U may be proper subset of omega d, this should be omega d. Now, answer the following questions. Decide which of the following are PDEs. Write down capital F as in the definition. How do you say somebody is a PDE? You have to go to the definition of the PDE, that involves a capital F. It comes with its domain, right. You should be able to give such a function f, and then this becomes a PDE. So, Laplace in u, the first one is dou 2 u by dou x square plus dou 2 u by dou y square equal to 0. Next is e power Laplace in u equal to 1, Laplace in u is defined above, and this is ux plus uy equal to sine of Laplace in u. This is ux plus uy equal to u composed with u. So, this circle stands for the composition of functions. Now, at this point you must stop the video, write down, you think about the answers, write down the answers if you have, and then proceed, because answer is going to come on the next slide. Okay. What are the answers? the f is r plus t, it is a second order PDE. E power Laplace in u equal to 1, f is e power r plus t minus 1, second order, ux plus uy sin of Laplace in u, f equal to p plus q minus sin of r plus t, second order, and this one is not a PDE. Okay. Think in your leisure time. If you do not get this answer, do not worry, keep thinking about this. Question motivated by the following example of Arnold in ODEs, dy by dx equal to y circle y, he says it is not a ODE. So, okay. So, the vague definition would allow this as a PDE, because it just says it should involve the unknown function and its derivatives, which this equation does involve, ux plus uy equal to u circle u. So, there is no point in admitting such equations if you cannot have a general theory for some special class of such equations. So, maybe that is the reason why Arnold called this as not as a ODE. So, if you understand the answer to this, the answer of this will be immediate. Now, we move on to classification of PDEs. So, what is classification? Classification of PDEs means creating banks with labels and associate each PDE to exactly one of the banks. Examples of a few methods of classification, we are going to see each one of them based on the number of equations, based on the order of PDEs, based on algebra. I will mention this details when we come there. So, question is it important to classify? Recall that a complete theory is available for solving systems of linear equations Ax equal to b, and the same is not the case with transcendental equations, which are also known as nonlinear equations. You have to hold each and every equation and analyze for solutions. Now, coming to linear ODEs, there is an oscillatory behavior of solutions that is different from first order ODE and second order ODE. Look at simple equation like y dash equal to y and y double dash plus y equal to 0, okay, or y double dash equal to y. Think of these solutions, some of them are oscillatory. So, it changes. So, it is important to identify a reasonably interesting or useful class of PDEs for which it is possible to obtain a larger understanding is possible. May not be complete, but at least a larger understanding, good understanding. So, for first order PDEs, we are going to see that classification leads us to uncover certain aspects of solutions, starting from the quasi-linear to the general nonlinear equations. We will see that in the next chapter. So, we will come back to this discussion on classification later on, also in chapter 3, where we are going to classify second order PDEs. We ask the same question and we have some better answers there, we will see that. So, now a classification based on the number of equations. Recall that a PDE is defined through a function of this type, right. If q is bigger than 1, it is called system. If q is equal to 1, it is called scalars. So, this is an example, is a Maxwell system of equations in 3 independent variables x, y, z and a time variable. That means there are 4 independent variables here, and E is a 3 vector E1, E2, E3, 3 functions, B is 3 functions B1, B2, B3, and dou E by dou t equal curl B, dou B by dou t equal to minus curl E, divergence of B and divergence of E are 0. So, this is indeed a PDE, you must write in this setup, and that is left as an exercise to you. As I told you, when q equal to 1, that is called a scalar PDE, but when q equal to 1, we also take p equal to 1. That means the unknown function also is a single unknown function. For this, otherwise what happens is that you have one equation, because you said q equal to 1. If you have more than one unknown, it means that information is conditions are very less. For example, just recall what happens with one linear equation 2 variables, not so much interesting, right. X minus y equal to 1, infinitely many solutions, that is one of the aspects. Okay. So, this is an example of a single equation, it is a very important example, we will be studying at depth later on. Now, second thing is the classification based on the order of the PDE. So, order of PDE as we know is uniquely defined and hence they may be classified based on their orders. This is a first order PDE, this is a third order PDE. Now, this is the important classification which uses algebra. So, this classification is based on the manner in which the unknown function and its derivatives appear in the equation. What are the possibilities? First possibility, dependent variable and all its derivatives whichever appear in the equation, they all appear as a linear combination with coefficients which are functions of only independent variables. That equation, such equations which has this feature will be called linear equations. Second option is highest order partial derivatives appear as a linear combination with coefficients which are functions of only independent variables and no conditions on the appearance of lower order derivatives and the function u. This may be called semilinear equations. Now, highest order partial derivatives appear as a linear combination, but now the coefficients depend on independent variables and also on the lower order derivatives including u. So, that will be called quasi-linear equations. The highest order partial derivatives do not appear as a linear combination at all. So, such equations will be called nonlinear equations. Now, you may ask this question, why only highest order derivatives are important for the last three classifications. They play a major role in determining properties of functions, is a vague answer. Okay. You should be in a position to appreciate this at the end of this course. Now, let us look at these equations, these two equations. One is the first order PDE and this is the second order PDE. What is common between them is that u and du in the first equation, u, du and dtu in the second equation, they appear linearly. Okay. It is a linear combination of those derivatives and the function. X and y we do not ask any questions. The classification is based on z, p, q variables. For the second order PDE it will be z, p, q or s, s tilde t. So, we will see very specific examples for first order PDEs, the classifications, and we will see most general possible equations that we can write of that type. So, linear first order PDEs means the unknown function and the first order derivative should appear linearly, that is coefficients are allowed to depend only on independent variables. So, they appear like this: axy dou by dou x plus bxy dou by dou y plus cxy u plus dxy equal to 0. So, this is an example. Semilinear, here what we ask is dou by dou x, dou by dou y should appear linearly. Coefficients are allowed to depend only on the independent variables and u may appear in any way, but not in the coefficients of dou by dou x and dou by dou y. So, therefore, the most general possible semilinear equation of first order is like this. This is an example. Now comes the quasi-linear first order PDEs. Here the first order derivatives dou by dou x and dou by dou y should appear linearly, fine. Coefficients are now allowed to depend on the independent variables as well as the lower order derivatives. If this is the first order derivative, what is the lower order derivative? That is function itself, they are allowed. So, therefore, this is the general possible quasi-linear first order PDE. This is an example. Now, a PDE which is not quasi-linear is called a fully nonlinear PDE. So, it is basically the complement of quasi-linear equations. This is an example, very important example, it is called Eikenel equation. Now, this is the picture or Venn diagram. First is linear, okay. This is the formula how the general linear PDE looks like. Linear is also semi-linear, that is a bigger class. Bigger class is quasi-linear. Out of quasi-linear will be full PDEs, this color in this color red color, but not in green, will be fully nonlinear. Otherwise, these are all general first order PDE will look like this. That was the definition. Now, for a linear PDE, first order PDE, f will be of this type, f of x, y, z, p, q will be like this. This is for semilinear and this is for quasi-linear. Now, we can ask the questions like which quasi-linear PDEs are semilinear? When this A does not depend on z, B does not depend on z, a quasi-linear equation becomes semilinear equation. Similarly, this is another question, please answer yourself. Now, we can classify the mth order PDEs. We have explicitly seen first order PDEs classification, but same thing can be done for mth order PDEs. What is the guiding principle? The 1, 2, 3, 4 that we have written down. How unknown function and its derivatives appear. If all of them appear as a linear combination, it is called linear PDE. If that is not the case, we straight away go for highest order derivative and ask how they appear. Then we had 2, 3, 4. So, we will write down here once again linear, see here mod alpha less than or equal to m. So, when alpha equal to 0, 0, 0, that is m equal to 0, the tuple alpha is 0, 0, 0, that means no derivatives, which means it is a function. So, here it says function as well as the derivatives up to order m appear as a linear combination, coefficients depend only on the independent variables. Semilinear, once again highest order partial derivative, that is mth order, appear linear combination, coefficients are functions of independent variables, rest however it appears no restriction. Quasi-linear, once again it is on the highest order derivatives, coefficients are allowed to depend on, apart from independent variable x, u, du up to dm minus 1, that is m minus 1th order derivatives. Then this is called quasi-linear. Outside that it can appear in any way they want, but as coefficients are the highest order partial derivatives, they can only be like this. Now, PDE which is not quasi-linear is called fully nonlinear PDE. So, Laplace in u, it is second order and linear, e power Laplace in u equal to 1, it is second order fully nonlinear, and this equation third order semi-linear. Of course, you may also say quasi-linear, but when I say semi-linear it has more information because semi-linear is much smaller set. This equation second order fully nonlinear. So, this is an exercise for you. Through examples show that the following inclusions are very strict inclusions. That means find a semi-linear PDE which is not linear, find a quasi-linear which is not semi-linear, and show that there are PDEs which are not quasi-linear. That means give an example which is not quasi-linear PDE. These are the questions for you, and thank you.